Normal distribution. An important distribution for continuous random variable is normal distribution. A random variable said to have normal distribution if its graph shape has a characteristic of symmetric and bell-shaped. So we looked at symmetric shape before in the previous section. Bell-shaped is describing this. So not all symmetric are bell-shaped. Note that, like for example, if you have a shape like this distribution, like say we have a histogram where it's just all same value, this is still symmetric, but this is not bell-shaped. So in this section, we're specifically talking about the distribution that is symmetric and bell-shaped. And this is the shape right here. In the middle, we have a peak, and that peak represents mean, median, and mode. And this is called normal curve. So let's look at some properties of normal curve. The graph of a normal curve is bell-shaped and symmetric about the vertical line through its center. So the mean, median, mode of a normal curve are all the same. And all occur at the center of the curve. And note that not all the data we collect are perfectly normal distribution. They have a bell-shaped and symmetric, so they're close to normal distribution. And there's an empirical rule where about 68% of all the data values of a normal curve lie within 1 standard deviation of mean. And about 95% of all the data values of normal curve lie within 2 standard deviation. And I'll explain what this means in a second. And about 99.7 of all data values of a normal curve lie within 3 standard deviation. That means 99.7% of data are less within mean minus 3 standard deviation and mean plus 3 standard deviation. So let's look at this picture to understand this properties. So here we have the mean value. And then within 1 standard deviation, whatever the standard deviation of the data set is, we add 1 standard deviation and subtract 1 standard deviation. Sigma, population standard deviation, subtract add. So 68% of data is here. 68% of data is here. And if you look at 95% is 2 standard deviation. So I add another standard deviation. Oops. Another standard deviation. So within 2 standard deviation from the mean and subtract another standard deviation. So in this blue section, there is 95% of the data. 95% of the data. And within 3 standard deviation, another standard deviation, another standard deviation, there's, so let me do this red one. Within this red, there is 99.7% of the data. The reason this is useful is we can find the probability in a proportion in a problem, but also it can help us spot an outlier. If you have a data that is greater than mean plus 3 standard deviation, like somewhere here, then it's an outlier. Okay. So let's first talk about how to interpret the normal curve. Normal curve is a example of a density curve, probability density curve. So we're just looking at the normal curve we saw earlier, how to interpret it. The area under the entire curve is equal to 1 because this is equivalent to the idea that probability of all the possible events is equal to 1. So area under the curve is 1. Any curve that represents probability distribution. And area between two values, A and B, has two interpretations. If it is the proportional population whose value are between A and B, proportion, or it is the probability of the randomly selected individual, A individual who have a value between A and B. And the region above a single point has a zero width, thus area of zero. Therefore, the probability of obtaining a specific value exactly is equal to zero. What this is talking about is because we're talking about continuous variable here, probability of selecting that one specific continuous data is zero because there's infinite number of values. So let's look at this example to understand how to interpret the probability within a density curve. Again, the density curve is just any curve that represents probability or some kind of data. So in this case, this is not normal, but the normal graph. This is not a normal graph, or this is not a bell shape. It's more skewed, right? But still, the way we interpret the area is equivalent to the way we interpret the area of a normal distribution. So, consider the probability density curve given above. Let's note one thing first. If I add all this area, add all together to 1. Add all to 1. So keep that in mind. If a value A is chosen at a random from this population, what is the probability that it will be between 4 and 6? So what this is saying, we're looking at this area right here, this blue area. Well, now it's yellow now. That area between 4 and 6 is 0.16. That means, let me write it here, means the probability of a randomly chosen value between 4 and 6 is 0.16. So if I were to randomly select the value for this data, probability of selecting a data between 4 and 6 is 0.16. So then if the value is chosen random of this population, what is the probability that it is not between 4 and 6? Well, we know that entire area is 1, right? So we can think as not, let me do probability not between 4 and 6. That's probability. Oops, should be 6. Plus probability between 4 and 6. If I add this to value, it should be 1. This should give us equal to 1. Well, we know that this is 0.16, so this value will be 1 minus 0.16. So if you do 1 minus 0.16, it gives us 0.84. That means if I add these two areas, let me shade with red, this area and this area, which actually goes forever. Well, it depends on the data. It might not go forever, but a lot of times it does because of the outlier. This area is 0.86. Oops, sorry, 0.84. I messed up the calculation there. 0.84. I wrote it correctly. Yeah, 0.84. Okay. So let's look at another example. The serum total cholesterol for males, sorry, this is for males, 20 to 29-year-old is approximately normally distributed. So it tells us that this data set is normally distributed, approximately normally distributed, with mean of 180 milligram per deciliter, sorry, and standard deviation of 36.2 milligram per deciliter. Based on this data obtained from National Health Nutrition Exam Survey, draw a normal curve with parameters labeled. So the parameter here is mean of 180, standard deviation of 36.2. So using this, because we know this is normally distributed, we can draw a graph. So here is the x-axis, and the mean is 180. And it's the peak, and we have a peak here, and we have a bell shape. And before I draw a bell shape, let's actually mark the standard deviation. Here's the one standard deviation plus the mean, one standard deviation minus the mean. So this number will be 180 minus 36.2. This number right will be 180 plus 36.2, which I put in a calculator, I get 216.2 and 143.8. Okay, so you can draw another dot here, bell shape. So let's draw a bell shape. I like to connect these two dots like this. And then it comes down. There's a curve. Make sure it's not a straight line. And draw an arrow when you sketch it. A lot of times implied. Even if you don't see arrow, it goes forever. Okay. And yeah, we could hypothetically label more standard deviations. But for now, this is good. Okay. So, second question. An individual with a total cholesterol greater than 200 milligram per deciliter is considered to have high cholesterol. Shade the region under the normal curve to right of 200. So right of 200. Let me use different color, 200. Well, 200, well, 180 is here, 260 is here. So 200 is maybe somewhere here. I'm going to use the same one to graph here. So 200 is somewhere here. And I'm going to shade this. So for B, I did on the graph above. Look at the graph above. This is answer to B. Okay. So from the same context, suppose that area under the normal curve right of 200 is 0.2903. We will learn how to find this area later. First, we're trying to focus on how to interpret the result. 0.2903. Provide the two interpretation of this result. So what does this mean? Okay, what does this number mean? I know in earlier here, I gave you two interpretations between A and B, but this also works for less than A, less than number, less than a number, or greater than a number also. So proportion less than number, proportion greater than number, probability greater than, probability less than. Okay. So two interpretation I'm talking about here is essentially probability and proportion. So what does this mean in terms of context of cholesterol level? What this is saying in that first, let's look at proportion. The proportion of males that are 20 to 29-year-old who have cholesterol greater than 200 is 0.2903. Okay, so let me write that answer. I'm gonna write the answer right here. So the proportion of males that have cholesterol above 200, 200 is the value, is 0.2903. So about 29% of male between 20 and 29 have cholesterol above 200. That's what this means. Second interpretation is the probability of selecting a random male between 20 and 29 who has cholesterol above 200 is 0.2903. So if we were to select one random individual in this data, probability of that random individual having cholesterol above 200 is 0.2903. So this is how we interpret normal distribution and probability. Okay. So just for practice, let's do another one. What happened? We have cholesterol. Let's say just for practice 150 and let's say 170, between 150 and 170. And I'll tell you that this area, again, we'll learn how to find this area later, but let's say this area is 0.15. Let's do 0.12. Okay, let me use different color maybe. Let's say that area is 0.12. What does it mean? This means probability of selecting one male in this population, selecting one male who has cholesterol between 150 and 170 is 0.12. Okay, that's one interpretation. Second interpretation is that the proportion of male who has or who have cholesterol between 150 and 170 is 0.12. So about 12% of population of male between 20 and 29 years old have cholesterol between 150 and 170. That's what it means. So let's summarize more of the properties of normal distribution. Normal distribution have one mode. The graph of normal distribution is bell-shaped and symmetric about the mode, or which also the mean, because the mean is also the center. The mean and the median of normal distribution are both equal to the mode. This means the mean, median, mode, and normal distribution are all the same. And empirical rule, which we looked at earlier, I think this is just better way to organize it. I know I drew it in hand, but I also want to show you the better organized version. About 68% of the population is within one standard deviation of the mean. So there's a mean value, add one standard deviation, subtract one standard deviation. Remember, standard deviation is a measure of a spread. 95% of the data is within two standard deviation. 99.7% of data is within three standard deviation. Okay. So the central question is, how do we find this area? How do we find this area? Mathematically, the way we find this area is one way we can find this using calculus. Although we don't need to know calculus here for our class, but that's how we find it. Every area we get, every mean and standard deviation we get, we can find corresponding area within normal distribution. Okay. But in order to make that process simpler, what we can do is we can turn any normal distribution into standard normal distribution. So what's standard? So the new word is standard here. What is the standard normal distribution? Standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. And what this allows us to do is we can use a z-score, because z-score refers to the distance from the mean. So in a standard normal distribution, z-score left of the mode or the peak of the curve or the mean, which is also say mean, are negative. G-score that corresponds to the mode or the mean is 0. Z-score right of the mode, the mean, are positive. So it's okay to have negative z-score, but it is not okay to have negative probability. Also negative area. That's not possible. Okay. So let me explain what this process is. Just quick graph. Essentially what's happening is we have a normal distribution of some sort, and each data has its own mean and its own standard deviation, right? Plus standard deviation, subtract standard deviation. But when I want to find the certain area, let's say this area, to find probability between two values, for example, finding the area every time often is not efficient. So what we do is we standardize, make it standard normal distribution by using z-score. Z-score. And what happens is that when we convert to this standard normal distribution, mean is 0 and standard deviation is 1. And the reason this is useful is we already know area of this in a table, which I will show you in a second. But that's the process we're doing. Each data has its own mean, but we're converting to the standard normal distribution. From a regular normal distribution, we're changing to standard normal. And in order to do that, we're finding the z-score, the distance between the data value and the distance between data value and the mean using standard deviation as a measurement. And standard normal standard normal distribution always has mean of 0 and standard deviation is 1, as you can see here. 1. So here's the areas of standard normal distribution chart. This will be provided. You do not need to memorize this at all. You just know how to use it. We call it cumulative because it shows the area up to that point. We'll do some example, but let's say z-score is point. Oh, let's look at in this table. Let's say negative 3.11. Then we'll look at here, negative 3.11. This is the area. That means the left side of negative 3.11, the area is 0.0009. That's the area. Which area we can interpret into proportion or probability depends on the context. Okay, so that's why it's called a cumulative, but we'll refer to as standard normal distribution from now on. But it's called cumulative because it's cumulative area. So it's a z-score when z is negative. This is when z-score is positive. So let's look at some examples together. Find each shaded area under the standard normal curve. So again, this is given this is standard normal curve. And here is 0 because it's standard. This is 0 here. So what this is asking to define is essentially probability, because area can represent probability or proportion. Probability of z, since it's left of 1.25, z less than 1.25. That's what we're finding. So how do we find this area? We go to the z table. So remember 1.25, z is positive in this example. So z is positive. So this is how we read this. Look at this number first. 1.2 right here. And 5 is the second decimal. Also right here. 0.8944 is this area. This as in this area right here. This blue area, this area right here is 0.8944. So we can say this is 0.8944. Again, what does that mean? It means the probability of selecting the value less than 1.25 is 0.8944. Or proportion of values less than 0.125 is about 0.8944. So about 89% of the data is less than 1.25. And 1.25 is 1 and 1/4 of a standard deviation. Right? Because this number is 1 standard deviation and 2.5. Whatever this data is 1.1 standard deviation and 1/4 away from the mean. Okay. So let's look at second. The second one says area right. This is very important because this one, the area is right side. But the table, z table gives us area left. The z table provides the area left of 0.36, which means z table can tell us this area. So what we can do is this will be 1 minus whatever this area is. In order to note this area, I can note it as probability of z less than 0.36. So the right side will be 1 minus probability z less than 0.36. So let's find that area. Let's find this area. Then we can subtract that area to find this shaded area. So remember 0.36. From the z table, we go to here, positive value again. 0.336. So 30, 31, 32, 33, 34, 35, 36. This right here. 6406. 6406. So this will be 1 minus 0.6406. Therefore, this area is 0.3594. So this blue region is 0.3594. Sorry. So what this means, the probability of selecting a value bigger than 0.36 is 0.3594. Or proportion of values that are greater than 0.36 is 0.3594. Okay, so let's look at third problem. Now we'll find this area using the z table. Now we have two values here. We want to find area between negative 0.71 and between 1.62. What we have to do is first, we actually have to find area left side of negative 0.71. So I'll find this purple area first. And then I find this red area, which is left of 1.62. And then I subtract the purple area. So let me write it here. First, we need to find z less than, because table only gives us area less than, left side of 1.62. So area left of this. And then I subtract area left of negative 0.71, then I can get this middle one, right? So that's what we're doing. Minus probability of z less than negative 0.71. So from the z table, we find each of these. So let's find 1.62 first. 1.62. 1.6, 60, 6162. 9474. 9474. Minus negative 0.71. Negative 0.77071. 2389. And then we get, subtract these two, we get 0.7085. So that's this area right here. Again, this means probability of selecting one data between negative 0.71 and 1.62 is 0.7085. Or proportion of the data between these two values is 0.785. So let's look at D. I'm going to actually have you try D on your own. So pause the video. And of course, I write the answer. So find this area, which is P less than negative 0.28 using the Z table. And this one will be area greater than, right? So in order to find this one, what we have to do is 1 minus P less than 0.94. Right, so think as if this is two-step. Find this one first, is the left area. You get a number. And find this one, then do 1 minus, you get a number, and add these two. Whatever these two numbers are, add these two. Okay? So pause the video and try. Okay, so from the Z table, I got 0.3897 for the value less than negative 0.28. And from the Z table, I got 0.8264 for less than 0.94, so left side of 0.94. So I have to do 1 minus to find the right side of 0.94, which I get these. So for the final answer, just add these two. Then you get 0.5633. So this means probability of selecting less than negative 2.8 or greater than 0.94 is this. Or proportion of data that are less than negative 2.8 and greater than 9.94 is this, 0.5633. So key ideas to find area under the standard normal curve. Standard. Sketch a normal curve, label the z-score or scores, and shade the area you're trying to find. Using the area under the standard normal table, distribution table, look up the area corresponding to z-score. To find the area in the left of z-score, use the area given directly from, well, I call it again cumulative is another name because the area is cumulative. We always remember that in this table is all cumulative. So this one, this is the same thing. So just find the area from the cumulative the table. Area right of z-score, we have to do subtract 1, as we did earlier, because the table only gives us area left side. For in between, we subtract smaller area from the large area. So large area minus bigger area. Oh, I'm sorry, large area minus smaller area is what we need to do. Okay? So let's look at more examples. Find the area under the standard normal curve left of z equals 0.53. So if you look at the z table, well, build a habit of creating a normal curve. And if this is 0, 0.53 is positive, so it's right side of 0. 0.53. That's right here. And we know that at 0, this line divides into half, 50%, 50%. So we know that when we're finding this shaded area, we know this should be greater than 50%, greater than 0.5, or greater than half. So from the z table, what we're finding here, left, we need to really pay attention to this wording, left, right, between. So probability of z less than 0.53 is what we're finding from the z table. So let me go to the z table. It was 0.53. 0, 1, 2, 3. I'm looking at this number right here for the second decimal. So 7019. So this is this area. Again, which means probability of selecting one number less than 0.53 is 0.719. Or the proportion of data less than 0.53 is 0.7019. The second problem, find the area under the standard normal curve right. Okay, you need to pay attention to this word right. That's why sketch the graph. For standard normal distribution, mean is always 0. This is negative 1.30. It should be left side of 0. So negative 1.30. So somewhere here. And we want to find this area. That means we need to actually find this area first from the z table, because z table only gives us value less than. So we're finding 1, we're doing 1 minus probability of z less than negative 1.30. And from the z table, this value is 0.0968. And then you get 0.9032. Again, so I found this from the z table. So make sure you know how to use the z table from the table, which will be provided to you for the quizzes and exams. Yeah. So this is not something you need to memorize. Z table is not something you need to memorize. Okay. So the third problem. Find the area between these two values. Standard normal curve. Here is 0. Between these two values. Well, one is 1.08, so right side of 0. Somewhere here. One is less than, so negative 0, less than 0. So we're finding this area. Well, so in order to find this area, first, we can find the area left side of 1.80, which gives us all of these, right? All of these. And then we subtract area left side of negative 2.83, which is subtract this portion. Subtract this portion. And then we left with only this red portion right here. Right? So that's the idea. So if I were to write with notation, we're doing probability of z less than 1.08 minus probability z less than negative 2.30. So we're finding these two z-scores and subtract from the bigger one minus smaller one. And remember, this area represents probability or proportion. Therefore, all this area should be positive. The z-score itself can be negative, that's totally fine, but the probability is negative, cannot be negative. So from the z table, This is 0.8599 minus this is 0.0107. Which I subtract, I get 0.8492. So let's summarize. We are finding this area of standard normal distribution. We can convert all the normal distribution to standard normal distribution by using the z-score, which we'll look at more into the next section. But for now, we'll really focus on interpreting these areas and finding this area using z-table. Area left of z-score, use the table directly. Area right side of the z-score, 1 minus the value from the table. In between z-scores, subtract from the larger to smaller. Oh, sorry, from the larger to smaller. So larger minus smaller is how I find the area between two z-scores. And interpreting it is proportion or probability.